And GRSS, it's, as Shmi has mentioned, is one among the 39 societies of IEEE. And the vision of GRSS is to be the leading society in science, engineering, education. And that's exactly what we are here for, and with all the young minds over here. And the thing is that it's truly global in the sense that, of course, we are doing remote sensing, so it's global anyway. And in the sense that it always has different varieties of different people coming from very interdisciplinary field. And that's what you can see here today with all the dignitaries over here. They come from various different fields, but we are united in this society of geoscience and remote sensing. So the day is packed with all nice events which has been scheduled and has been coordinated very well. And I thank all of you to be a part of it. Thank you and have a wonderful day. Thank you very much.
Thank you so much, sir. Without support, this day wouldn't have been possible. I request now my sweet friend, Dr. Feroz Chamboli, to share her few words.
Thank you, Musmi. Hi, everyone. Welcome to the Student Young Professional and Women Congress. It's an honor for me to be here today, and I'm looking forward to interact with all of you and get to know more about the KL University. So I want to thank first Musmi for organizing this event and inviting me and doing all this great job. So thank you. And I want to thank the principal, Dr. Rama, for supporting us and having us today. And so we at IEEE Geoscience and Remote Sensing, we are a global community, and this is one of the most powerful aspects of this society. So we have a global community that stretches across all continents, and this is very important in every career. So we help students and young professionals to have many connections. They can be your collaborators, your mentors, or even your friends in the future. And this event is a great opportunity to make those connections and talk to people and
of their presence in the event. We'll go for the felicitation ceremony, and I request our principal sir to come on the stage and felicitate all the guests. I request Shobha and Rai to come on the stage. I request Ramakrishna sir to felicitate Dr. Keely Ross. Yeah. I request Principal Sir to felicitate Dr. Mihai Datsu. I request Sir to felicitate Dr. Feroz Chamboli. I request Sir to felicitate Dr. Abir Bhattacharya. I request Sir to felicitate Dr. Shobha Pernisami from Anna University, Chennai. I request Sir to felicitate Rahisha. She is the Region 10 Student Chapter Coordinator for IEEE GRSS. I request all the dignitaries to come forward for a group photo. Thank you so much, everyone. I request everyone to occupy the seats. I take this privilege and honor to express my gratitude to each one of you here to propose vote of thanks for this inauguration session. Not only across the India, we have from the Hyderabad section, we have so many volunteers who have specially joined today only for this inauguration session. Dr. Rajesh Tiwari, Dr. Saindar sir, Dr. Vijender sir, Khalid who is already a student YP member of IEEE GRSS, Dr. Hitesh Sharma, and in this event there are 9 student branches who are technically co-sponsored for this event. Lastly, I again thank I did not, sorry Lakshmi, I did not get your name, Bhargavi ma'am, and it is an honor to have such a gathering at KLH, and I really cannot express my sincere gratitude to Arpita ma'am and to Ramakrishna sir for continuous support towards this event. Thank you so much.
We are pleased to welcome Ms. Rashisha Totoli, Research Associate at a Spatial Computing Laboratory, IIIT, Bangalore, with a strong foundation in civil engineering and geoinformatics and a PhD thesis in spatial data science. Her work spans land change estimation, spatiotemporal data mining, urban science, and AI in climate strategy. She also serves as an IEEE GRS's Regional Chapter Coordinator and actively supporting regional initiatives. Please join me in welcoming Ms. Rahisha Totoli to the stage for her session on GRS's student branch opportunities.
Slides will consider. Next slide, please. Yeah, thank you so much I should thank Mausmi ma'am for inviting me here and be part of this program. So before that, the best part is introducing myself is better than someone else. I am a civil engineer. That Dr. Avik sir was saying that it is a completely, GRSS is completely interdisciplinary. I am the best example here because come from a civil engineering and geoinformatics in master, and now I'm doing in data science, spatial data science. It's completely a new emerging topic. Yeah. New emerging topic, I should say. So I have completed my PhD. I'm waiting for my defense, and my work is more into how these spatial technologies can be utilized for urban challenges. Like as in urbanization, you may all familiar. Like it's a common topic. So there are many challenges with urbanization. I'm just because I know the topic. Today's topic is more into agriculture and agri-food system, but I just want to focus little bit that I am doing something different from agri because as this is an interdisciplinary and the spatial technology is a vast, like there are a lot of domains are there within geospatial technology. Then, apart from my academic background, I am a part of GRS's global activity. I am an Indian RCC, that is Regional Chapter Coordinator for India. Then the best part, why I am here, I just want to show some example how I just grow up in GRS's family and how, from membership to leadership, I should say. Like because I started as a member in GRS's, as you all are a member, right? So what are the opportunities you have as a member, and what are the things these technical the communities are doing? I just want to show some real example with myself. Then recently, last September, I visited Italy because of the GRSS activities and all. Italy because I went for attending some summer school because like I'm improving. I am just improving in my what I should say, that learning system. It's because always we should learn, right? We should not stop learning. So I have attended the summer school. It helped me to understand how these deep learning technologies can be utilized for different applications. So there are a lot of international conferences and regional level conferences. I get an opportunity to work as a volunteer and organizing these kind of conferences. Then a lot of things. I will tell you one by one. So why I am here, I'll just little bit brief about what these GRSs are doing and global level and regional level, and from membership to leadership, how you can grow with by checking with the GRSs activities. So welcome to GRS's global activity. Now, as you all are a member, now you are in our family, like you are in our community. So I will just show you what are the things happening within our community and just explore by yourself. So as a global activity, has GRSS tackle a lot of it interdisciplinary, because you can see here, it's a global scale and developing instruments, methods with a worldwide coverage and coordinating ground. And that what is meant by that? There are a lot of things, because urban is a one disciplinary and one is more into disaster management, water resource engineering, agriculture, climate science, a lot of things, a lot of different domains are within GRSS. And global relationship means we thrive on relationship with people and organization world. Here you could see, right, from US, from Germany, from India, a lot of collaboration is happening, a lot of research is growing. Okay. Then when you see the number of chapters in a global level, you can see there are currently 70 chapters and 30 student branch chapters and 12 ambassadors. Just a global picture of this. You can see the red pixel, like red dots, right? So the red is representing us all. Then chapters representing GRSs at the regional level, providing a platform for members. That is how it's happening here, right? So the platform for members to engage in geoscience and remote sensing activities. Then they offer a supported network opportunities, like you will have a chance to meet those who are expert in this field, and you will get friends within the network, so you can grow yourself. Then when you see the statistics, India region, you can see that in Bangalore section, we have right now we have 8 chapters. No, it's like a little bit older. Right now we have 10 chapters inaugurated, and 2 we are going to inaugurate in the next December. No, this coming like next month. So you can see some statistics here. Hyderabad have 17 student chapters, and yeah, this is some statistics all over the India. So student chapter 47, 7 symbol chapter, and John chapter 1. Then here I can tell you something regarding my journey with the IEEE GRSs. So this is a little bit story behind Bangalore chapter, how it has gone. Dr. Deya Sagasar they have developed, the team has developed this GRSS chapter in long before. Now we have the statistics. 2020 there was only 37 members, and now currently we have yesterday when I was checking the statistics, we have 265 members in yesterday. Then 114 in 2023, and within 1 year you can see, right, because the people knows that these are the things happening in this GRSS community, and 265 in 2024. And in the case of a gender, the diversity also you can see now 30, this is just a case of Bangalore section. There's 38% female and 50, it's almost 50, right? Gender equality has come closer. 53.55 male. And these are some student branch chapter information in Bangalore section. Yeah, here. In 2022, I got a chance to work with Bangalore section as a student activity member, and I got a chance to organize some kind of a Mapathon event with the IC Hack, then IEEE India Council. We were organizing that. So what was the main intention is that because from computer science, from different streams, engineering students, we just want to make sure that what is happening in GRSS, and we were just giving some kind of a demo with a new platform, Google or Google Earth or some kind of a tools we were introducing to the students. So this helped me to grow further because I got that GRSS is doing a lot of things, and I got a chance to participate and present my paper with Ieee Grss 2023 and meet eminent people in GRSS family. And I was volunteering there. I got a chance to work as a session manager. A lot of opportunities within GRSS. So that is what I want to highlight here. All the all the things you will know from the website. But what was my story? That if some students get motivated, so this will help you further to grow. See, this you can see, and I was being part of the booth, because we were conducting Ieee Grss conference in India last year, 2023 December. So, but this is happening in 2023 July. So I got a chance to showcase it helped me to publicize the Ieee Grss work, and we got a lot of publication. It was a huge success, I should say. And Mumbai section, yes, Avik sir was there in that Ieee Grss 2023, and we were doing it wonderful work with Ieee Grss. And this you can see, I was part of Women in Engineering program and technical activities. This is in Ieee Grss, which happened in IIIT Bangalore. Then apart from all this, we have done a YP event, YP hackathon, like how this geospatial can be useful for different work. And we have conducted a lot of hackathon. It help us to attract many students, younger students, and they have participating in these kind of events. They were like after these events, they got know that they got a eagerness to get know what is next. So they have keep on tracking with a different hackathon after this program. Then apart from all these things, we were part of Let's Talk Spatial, and we were going to some institutions or some kind of industry, because it's a kind of a joint event, like industry also were participating here, and we were going to some institutions or industries, and we were giving talk and understanding this geospatial technologies importance in this current era. And YP activity, you can see we got a best local YP activity award from this global level, and Bangalore chapter was a runner-up there. And you can see there are a lot of things are happening in GRSS community. You can see distinguished lectures are there. The best part is that if you people are a young researcher, you will get a lot of expert talks. It will be recorded. Recorded will be there. Suppose you missed the chance to hear that, but you will have a recorded version of distinguished lectures. And I got a chance to showcase my work. That is how it happened. So I was being part of that program, and yeah, I remember Khalid is here. Yeah, Khalid has given this chance for me to show this work. And yeah, YP is doing a lot of work within GRSS. And not only this distinguished, they are doing a lot of hackathon programs and a woman mentoring program. Yes, I remember Mausmi ma'am was leading this woman mentoring program, and I met during Ieee Grss 2023. I was a mentee there, and Mausmi ma'am told that after doing your PhD, you should be a mentor. I still remember that those days. It was 2 years before, but still I remember those days. Yeah, then recently I went to Italy for attending the summer school. Then fully travel grant. Like it's like whenever you attend these kind of a conferences or kind of a summer school, GRSS can support with some kind of a travel grant as well. Students will get a lot of opportunities to travel worldwide and expand your knowledge. So this is how my journey comes. Started as a simple IEEE membership, and my professor asked me to take a GRSS Society membership. Then during my PhD, I started as a career with GRSS membership. Then I got a chance to work with different volunteering jobs, different talk or different kind of work with the GRSS. Then how it grows. Like I have given a lot of lectures to the students, like not only the researchers. I went to schools, like high schools or even higher secondary. They were looking for like what is next. They want to know what will be there after 10 years, what are the leading topics. I was conducting some lectures, and from this is industrial, so you can see here. This is industrial, some kind of collaborations. We were giving some kind of lectures to this L&T team, and got a chance to work as a global Ieee Grss. Then now I am here, okay, because I just want to show these things, like this is happening in GRSS family. So tomorrow anyone can be in this position. You can show your work, or you can be as a leader in this GRSS family. So little key notes that what you will, like after a membership, you should not keep quiet. Like you have to search what is happening in GRSS, what are, maybe every month some kind of lectures will be there, and the past lectures, and who all are there in this community. Then you can see my experience. I got a lot of experience how to handle this, organizing a team, organizing a conferences and meeting people, and because many people, like one person will be good in expertise in one domain. So you have to match your knowledge, because it's not only volunteeringship. Parallelly, you are learning something within your research, and you are growing your research career, and a lot of things. Then women mentoring program, it helps a lot with those who are facing a lot of difficulties in the, like, how to balance the personal things and the professional things. Apart from your supervisor, you will get a chance to get one more mentor somewhere from someone from global. So they will, not only the research, like some kind of motivation sometimes required for a woman, right, to push forward. So that will help you. This program will help you. I was part of this women mentoring program. Then GRS's idea, Moshi ma'am, I was doing a lot of things with the idea, and I have applied. I got a professional development micro grants of 500 USD. So every year this will be having. You can also apply these kind of things. Micro grants will be, but just doing membership cannot help you. Just check it when the call comes. You should apply, and just discuss with your supervisor what is next. Maybe you need some guidance how to go further. You should apply, then only you will get it. Nobody will come and just search you. Is there any people are looking for a fund? No, that won't happen. You should keep searching. You should apply, wait for a good time, okay? Then conference support, yes, this is the best part, because students, if they are not able to travel globally without the minimum fund or something, GRSS will give you a student travel grant with all the support, okay? Then I guess apart from the travel grant, there is a chance to work as a volunteer, as a session manager for us, because conference charge you a lot of registration cost, right? So you people may face a lot of difficulty in registration if the university is not having enough fund. But if you are with the GRSS and if you are doing a lot of volunteering job, this team, GRS is doing like a kind of a grant for a session manager. For me, I could get a 400 USD from a GRSS, as I was working as a session manager for 40 hours or something. Then it covered my registration cost. That's what I want to say, that I didn't take it from my pocket. And the best part, IIDF for summer school, September I visited. The entire amount has granted from travel, there's a GRSS family or GRSS society. And next month, December 1st to 5th, there is a Ieee Grss 2024 is happening in Goa. Those who are interested to participate in this kind of a network opportunity and to know what is happening in GRSS, you all are welcome to be part of this Ieee Grss 2024 as well. Please do just visit this website and see what is there in the schedule and all, okay? And as you all may be a membership, what are the kind of memberships available? Apart from student membership, we have a full membership for a professionals and a senior membership, those who are 10 plus years of being in a GRSS community, and you can nominate yourself or your seniors can nominate in the senior membership, okay? Then anyone is interested how to get a student branch chapter. It's a very normal process. Like you should have a minimum number of 6 students, and you can just scan this website. It will be having all the information that how to file your petition for student branch chapter. Yeah. That's all. I'll be here for the whole day. So those who are interested to be part of membership, be part of a GRSS, how to file your petition for a student branch chapter, please feel free to contact me. I am there in LinkedIn, or I can anytime I can get in touch with you. That's all, and welcome to GRSS family. Thank you so much.
Thank you, Ms. Rahisha Totoli, for sharing valuable insights into GRHS student branch opportunities.
Sorry for the interruption. First, I would like to invite Avik Bhattacharya sir to share an opportunity of the Ieee Grss 2024.
Yes.
So thank you very much for this presentation, Raisha. So as Raisha mentioned, we had the INGARS, the India Geoscience and Remote Sensing Symposium. It's specially meant for the region because many people, we have trouble, of course, traveling to places for attending. So now there are these regional geoscience and remote sensing conferences, which are happening in many regions. India is one of them. We had from pandemic time, we had 2021, but it was all virtual. We had the first one last year in Bangalore, which Raisha mentioned, 2023. But I would like to mention that this year, also in next month, we have the INGARS conference in Goa. I would say where is it? Yes, so Mukta. So just to introduce you to the people who are in charge of INGARS 2024, Dr. Mugdha and Dr. Varsha is here today. If you would like to be a part of it, if you want to attend the conference in Goa, it is from 2nd to 5th of December. But it's not late. You can still be a part of it. And if you want to say a few words about it.
Yeah. So if you are interested, let me know. The registrations are closed, but if you all are interested, we can reopen the registrations. And it will be a wonderful opportunity to interact with GRSS student members, GRSS researchers from all over the world. So please do let me know if you are interested. You can check out the website for INGARS 2024. Thank you.
Yeah, thank you very much. So they will be here maybe till the evening. They're here. So maybe during lunch or sometime, if you want to discuss anything and want to see how to participate and kind of be a part of it, please do feel free to interact with them. Thank you very much. Thank you.
Thank you so much, Rauk sir. I hand over the mic to Charishma.
Thank you, sir. Thank you, ma'am. Thank you for the great information. Now, please join me in welcoming Mihai Datsu to the stage as he presents artificial intelligence for Earth observation with respect to the agriculture.
Okay, so I will continue with a short presentation on artificial intelligence for Earth observation. I will start with a movie. The movie has no, I will let the movie running without any comment. Just watch the movie. It's 30 seconds. So climate change and climate change adaptation. So we feel the effects of the climate changes. In the couple of last years, that is evident. We are doing measurements, in situ measurements, over all the Earth, but the only way to monitor the Earth is Earth observation. So Earth observation is the only global and perpetual observation. So we need to use the satellite images. So the main factors is a neck. Yes. The main factors in climate are the ice, the polar calottes. That is a movie showing how a glacier is melting. It's a TerraSAR-X, the German satellite images. And the next very important factor in climate change, it is the next rainforest. It's a time series in the rainforest, which are both glaciers, polar areas. They are keeping the balance in between the carbon. I will continue with another short movie. This time I will let the original sound of the movie. The movie is the previous one.
But it has the sound, right?
No sound. Yes, I present the movie. So this is a German aerospace digital archive. These are the processing units, the satellite signals and transform Earth observation products. We have to store hundreds of petabytes of data. The volume is growing with the number of satellites. This data must be perpetuated. So we have now observation over 50 years, and we have to maintain this data for the future. We copy the support to another support because we have to adapt to the IT technology storage. However, all this data is digital. Inside the data, we cannot see. We have only binary. And actually, the problem we have with this big data, which is exploiting the content, is to transform this in something meaningful. And as it is immersive visual data mining, the students, the PhD students, they are inside the cave. They are surrounded by the images. When he's looking at an image, he will attract all similar images in front of him. So this is a new technology to exploit this, the value of the huge volume of the data in these archives. So this is actually the technology. So this is a. So this is a technology. Yes, it's working. So this is a technology to. Yes, this is a technology we are using to exploit this information content of huge amount of data. So next slide, please. So I start with acknowledge. I acknowledge my colleagues, the team at DLR, the German Aerospace Center, my team at Polytechnica in Bucharest, and the team at CNAM, the Conservatoire National Art et Métier. The next slide. The presentation is about artificial intelligence on Earth observation. And the next slide. So we are facing the effect of climate change. So we are facing a pressure on population growth, which has an impact on resources like fresh water and food, stress on land and marine ecosystems, environment pollution, impact on health and biodiversity. And actually, the effects of the global warming are rising the sea level, increasing the level of ocean acidification, and frequent and extreme events such as flood, heat, and waves. And actually, in this moment, to face all this, to extract the information from the big data, we have a new technology, a new technology which goes beyond big data and goes beyond artificial intelligence. This is a technology of digital twin Earth. So digital twin Earth will integrate information extraction, visualization, modeling, simulation, prediction, forecasting, in such a way to give an image of the effects of the climate change. So the next. I give a short presentation of a project I started recently. It's a project to establish a competence center on climate change adaptation. Climate change adaptation is a very broad field, and we focus on one of the most important aspects. It's a climate change adaptation at a human scale activity. This means to observe phenomena and to learn at scale of 100 meters, not at a global scale like climate change, and at the scale of days and months. So these are the scales of human activity. The next slide. So the competence center will be a unit of Polytechnic and Bucharest, establishing a national network of excellence and connecting at the European level. And to make this competence center actionable, we develop digital media. The digital media, it is a federated system of digital twins. A digital twin on climate, which is extracting information from satellite data, digital twin on health, monitoring mosquito and diseases carried by vectors, a Black Sea, water quality, extreme events, and biodiversity. The next slide. To build these digital twins, we need a new technology, and this new technology, it is artificial intelligence. And artificial intelligence for satellite data is different from artificial intelligence in other fields like computer vision or multimedia. The next slide. So actually, it's a very brief introduction in remote sensing. So I present the sensors, the information extraction in remote sensing in three directions. One direction, it is information in patterns and objects. The other direction is information in physical parameters and information in geometrical parameters. So we have sensors which are extracting information in very high resolution and can recognize airplanes, ships, containers. But we have sensors which are extremely spatialized. They extract sometimes a single physical parameter like ozone concentration, for instance, or sensors which are measuring geometrical parameters like the height, elevation of the surface, or the displacement of the surface. So next slide. Information is physical in Earth observation. So it's not a picture. We do not have photographs. So we have a satellite image, Sentinel-2, Copernicus, the color image from the multispectral selection, in which you see the cloud, the Danube, the Black Sea, and the agricultural fields. And from the same image, we extract the infrared band. So what happened? The cloud disappeared. Cloud is not anymore here. Why? Because it's an infrared, and the wavelength is larger than the particles, and it's a diffraction process. But the cloud shadow is here. Why? Because infrared is measuring temperature. It's like feeling the temperature on the ground. So it's an example on physical information extraction. It's different from picture. Synthetic aperture radar. We have the Apache Railway in California. The railway is making a loop because the terrain is very steep. That is the TerraSatix, the German satellite, and this is a train. Why? Because the train is moving, and the microwaves are reflecting on a moving object, and they are, and the echo has a Doppler change. So again, a physical phenomena. I choose only two examples, optical and SAR, to demonstrate that these are not pictures. So satellite images are records of physical signature of Earth. And in here we proposed a paradigm for physical information extraction in artificial intelligence. So we embed the knowledge, the simple concept it is embedding the knowledge we have, the domain knowledge, the physical knowledge, the parameter we know, in the physical process. It makes no sense to train a network for all the parameters as long as we have an order. And these models are physical. We need to learn the physical parameters. So we need to deal with the wavelength. We need to the image formation. We need to the type of scattering of the data. And later, the parameters which are not known, we learn it from the data. So we deal with models and models which are generated from the data. Physical models and artificial intelligence model trained from the data. So that is one example of such a network. So these networks, like deep learning, they are adapted for the synthetic aperture radar. So we have 3 parallel lines. One line is learning like a classical with a limited training data set from the detected data. And we have 2 lines which are learning from complex data. Why? Because in the complex data, we have embedded the model of information. And we have the complex data learning and learning in the Fourier transform, the extracted spectrogram. So we're using all the information about the model in image formation to extract the next slide. And what we obtain. So that is Paris. That is a quad pulsar data, which has a spatial signature. We train the network with quad pulsar data, and we apply it to single pole. So we generate a virtual sensor. We generate a signature which was not observed. Why? Because the model is learning latent space, the basic property of the scattering and the image formation, and we can generate an unobserved data. We can predict the data. So next slide. In the same way, we apply this for the spatial case of polar ice, important in the climate, where we can do a classification like water bodies, floating, iceberg, glacier, but we explain. It's not enough to have labels on the data. We need an explanation, a physical explanation. And the physical explanation is coming from the scattering model, and we have each of the classes marked like diedral, dipole, break, double reflection. So compared with computer vision, we make a classification, but we explain it in terms of physical parameters. So this is another example of adapting convolutional network for the nature of complex value in SAR data. So we have 2 architectures, a convolutional network and an autoencoder. Both of them, they are implemented on complex numbers, both in algebra and statistics. And what we obtain? We obtain a network which is learning from complex data. But it's learning from the complex data how? Preserving the physical properties. So it's more than complex data. It's a physical process of synthetic aperture radar. So the generated images, they preserve coherence, and they preserve the subaperture decomposition. So it is more than a deep learning for complex, it's a deep learning for synthetic aperture radar. And now I go on an application on optical data. So one of the hindering factors in optical remote sensing, which is important in climate and agriculture, it is the atmosphere. Atmospheric effects like fog and clouds, they hinder periodic observation. And this is a network which is able to remove the effect of fog or smoke and reconstruct the data. So it's not a generative model. It's a model which is based on a physical process exploiting the infrared information, which is penetrating to the fog or clouds and reconstructing the data. And I go now to the time series. So today, Earth observation, it is not anymore producing images. Earth observation is producing time series. So the satellite is coming periodically. Typical single satellite comes at about 10 days over the same place. And we obtain a time series. We can, no, if you can go to the movie. No, back on the movie. If you click on this image. Yes. So this is 30 years of observation of Bucharest with Landsat from 84 to 2012. So we have a data cube. We have a whole history. It's a big amount of data. And in time series, we need now to do 2 things. First, to extract the information from such a data cube. It's a high complexity information. Visually, we cannot cope with this. And after 30 years of, or 50 years of remote sensing, we have thousands of images moving from space. And the second, in remote sensing, the users, they want to have very frequent observation. This means to use multi-sensor. And if we are using multi-sensor, combining synthetic aperture radar, which is independent of the cloud and illumination, and optical, we face a problem. Information in multi-sensor could be contradictory. So we could have the same land cover with different instances in different images, and the fusion will not work. And in this case, we go and propose a paradigm of data fusion, like early fusion, mid fusion, and late detection. And in this, we introduce in the architecture the next level of attention. And this level of attention is learning actually the contradictory aspects. And the one which are positive, which are combining and they are enhancing classification. Because if I try to make data fusion in a simple way without analyzing the positive and negative contribution in the data, I cannot obtain a better result. And in here, the deep learning is using latent space with an attention, which it's detecting as a contradictory. I will go to the next slide. And these are examples for classification of agricultural fields. And in here we have for the multispectral and SAR the highest attention. So these are the areas where the attention detected similar examples, increasing and giving similar classes. And we have the most important part, the lowest attention. In here, these are the contradictory parts. So these parts are excluded from the learning, detected automatically. Why? Because if I have some folk trying to be fused to the SAR, that will create a confusion. The next slide. And I'm almost at the end. It's another approach on artificial intelligence. Sometimes we have sensors which are producing very precise and important measurements, like the Jetty from NASA, which are measuring its LiDAR, measuring the height of a canopy. But the sensor is not operated continuously. It's sparse in time and it's sparse in location. And we train deep learning on Jetty, and we apply on Sentinel-2. And what we obtain? We obtain the height. We predict the height of the vegetation. So yellow means high vegetation, blue, low vegetation. We predict the height of the vegetation from Sentinel-2. And advantage, Sentinel-2 is a continuous observation, global. And now we have a virtual sensor is generating a parameter which was observed by another sensor and transposing to this. So these are the important aspects which were not possible before artificial intelligence, and they are referring to physical parameters. Now, artificial intelligence is dealing with two types of models, predictive and generative. Previous models have been mainly predictive models. Now I go to the generative models. And for the generative models, we have the problem of reconstructing corrupted bands. So satellite images could have corrupted bands uncalibrated, or some artifacts in the sensor. Could also happen that we want to have a spectral band on a wavelength we do not observe. And in this case, we can define architectures which are learning from a certain data set and predict a spectral band which was not observed. Again, a virtual sensor. And we apply this next to Sentinel-2, in which we can predict and correct the bending effect, the calibration effect in the data. And when we predict in Sentinel, because Sentinel has bands at 60, 20, and 10 meters, we predict all missing pixels. And all missing pixels means to obtain the super resolution. So we change super resolution in a prediction, like pixel which have been not observed. And we obtain from 60 meters the 10-meter resolution. And this 10-meter resolution, super resolution, has a property. It's preserving the physical properties. So if we compute spectral indices from these predicted bands, these spectral indices are calibrated, they preserve the property of the sensor. This is an architecture for super resolution. And in the architecture of super resolution, we include the modulation transfer function. We know the system, so we design the sensor. And including the modulation transfer function, we can generate a super resolution which is preserving, again, physical properties. We apply the VAL protocol, and with the VAL protocol, we are able to include a forward model and to obtain the super resolution. And these are examples of super resolved images from 60 meters to 10 meters, again, with the property to preserve the spectral indices. Again, a physical property. Here's the next slide. So I'm at the conclusion. In this project, we went on a climate change adaptation at the scale of human activities. This means compared to his climate change models at scales of 10,000 kilometers and tens of years, hundreds of years. We want to model phenomena at the scale of human activity, 10 meters, 100 meters, and a few days. And that is one of the most challenging, and it's a niche field we developed. Thank you very much. Thank you for attention.
Thank you, Dr. Mihai Dacu, for an insightful talk on the role of AI in Earth observation for agriculture. Please feel free to proceed with our tea break and take this opportunity to network with your colleagues. Thank you.
Should I announce?
Everyone, please feel free to use the refreshments at the behind, and even we have a photo booth to take the photos. Thank you.
all the guests are here. I know many of the participants are willing to take selfies or the photographs with different guests. There is a photo booth also there. Just utilize the photo booth and create as much as memory you can.
I request all the guests to please occupy their places. I request all the guests to please occupy their places. We are going to resume the session soon. I request all the guests to please occupy their places. We are going to resume the session soon. It's my humble request to all the guests to please occupy their places. We are going to resume soon. It's my humble request to everyone to occupy their places. We are going to resume the session soon. We are going to resume it now. It's my humble request to all the guests to please be seated. We are going to resume it now.
At this moment, I would like to invite Dr. Shobha Periyasamy from Anna University to the stage to her session on innovation in microwave remote sensing for enhanced decision making in agriculture.
Very good morning to one and all. So thank you. I would like to take this opportunity to thank IEEE Hyderabad chapter, Kale University, Professor Mausimi, and the principal for having invited me for this presentation on the most emerging topic, agriculture. Because, using technology, we have gone to the moon, back. However, we have ended up at one point where we realized that there is no life without agriculture. So in recent times, we started exploring the potential of the recent technologies in the improvement of agriculture. So my topic is innovations in microwave remote sensing for enhanced decision making in agriculture. So innovation I'm talking here is innovation, not invention, because whatever the simulation we develop from microwave remote sensing, it has been well implemented by the researchers across the world. So all of our inventions have become innovations. So I'll start my presentation. So you have to understand that microwave remote sensing is not like superior to optical remote sensing, but it is a complementary data product to optical remote sensing. The method of acquisition, processing, and the understanding of microwave remote sensing is a little bit different from the optical remote sensing. But obviously, it is a complementary data product to optical remote sensing. Whenever the optical remote sensing may not able to work properly, you can make use of microwave remote sensing. So I'll be only focusing on synthetic aperture radar. It is a type of active microwave remote sensing data product. So in which the sensor will be capable of sending a series of signals at different frequency level towards the surface. Once the signal reaches the surface, the signal will undergo a lot of changes, polarization, based on the polarization, moisture, roughness, or there are a lot of properties. So it will undergo changes. So after this change occurred on the surface, the same sensor will be measuring the signals that are scattered back from the sensor. That is why the unit in microwave remote sensing is backscattering. Some of the signals will be scattered back from the scattered back from the surface that will be measured by the sensor. So that is why the unit of microwave remote sensing is backscattering. So as I told, like the signals will get changed based on several parameters, especially roughness and moisture. That is the basic parameter through which the signals will get altered. The polarization state will get altered. The electric properties of the signal will get altered based on these parameters. So usually, synthetic aperture radar, it is an enhanced form of microwave remote sensing data product because in earlier days, we have side-looking aperture radar in which we have found some difficulties. So it is an enhanced form of SLAR. So if you want to increase the resolution of the synthetic aperture radar, we have only two parameters, as I pointed here, wavelength and antenna length. If you want to increase the resolution of synthetic aperture radar. So if you want to increase the resolution, either you need to decrease the wavelength or increase the antenna length, right? So if you decrease the wavelength, then it won't be a microwave remote sensing data product. It will be similar to optical remote sensing. So we cannot do that. So the other choice is we need to increase the antenna length. So just assume that physically it is not possible to have such a long antenna on board, right? So in order to overcome this issue, we have actually increased the antenna size, virtually increased the antenna size by observing a same point from different location on the same straight line. So that is why it is called synthetic aperture radar, which has high resolution in both range and azimuth direction. So potential characteristics of microwave remote sensing. So for any kind of agricultural application, you need time series data. Because if you get a single data, you can able to analyze something that I can understand. You can able to analyze something. But then if you monitor some phenomena, some important phenomena, because in agriculture, a continuous monitoring is very important before you go for any decision making. So this continuous observation is sometimes lagged in optical remote sensing because the optical remote sensing is being attenuated by atmospheric interferences like clouds, water droplets in the atmosphere. So we cannot use optical remote sensing all the time. So when you need time series data, then you have to definitely microwave remote sensing because in microwave remote sensing, we are using longer wave bands. So it will not be attenuated by atmospheric particles and atmospheric disturbances. So this observation can be done irrespective of weather and time. So continuous observation can be made. So for agricultural applications, you can use microwave remote sensing without any doubt.
you can use it. So the first one is, it is free from cloud, right? And it has higher potential in phenological applications, like paddy phenology you can able to monitor because you have continuous data, continuous observation, you can perform continuous observation. So it has higher potential in phenological assessment. And there is a technique in microwave remote sensing. What happened? Yes. There is a technique in microwave remote sensing called interferometry, through which the displacement can be effectively monitored or measured based on the phase shift. So this phase shift can also be applied to find out the height of the crops. And this is the most recent studies, there are a lot of recent studies have emerged to find out this phase shift, or to use this phase shift to find out the height of the crops. And dielectric properties, because we are dealing with signals, so definitely there is a loss in the signal, or based on the moisture content in the soil, there is a change in the dielectric properties. So this particular dielectric property can be used to assess the soil moisture and soil contamination to some extent. Not all contaminations can be studied from microwave remote sensing. You can go up to salinity, to some extent fluoride, and it has not been explored so far. So salinity has been well demonstrated. And most importantly, soil texture, because soil texture is the most important property that defines the water holding capacity of the soil, and it will be very useful for the irrigation management. So this soil texture mapping can be well done from microwave remote sensing simulation. I'm just only talking about the simulations, empirical simulations. So SAR data, when you take any SAR data, it is being influenced by target and system parameters, 3 target and 3 system parameters. When you look at the target parameters, when you look at the system parameters, wavelength, frequency, polarization and incidence angle, on which you don't have a control. It will be supplied by the processor. You don't have a control over it, right? Whereas when you look at the target properties, just look at the target properties, soil moisture, the dielectric constant, topography, and most importantly, geometrical orientation. So in microwave remote sensing, the data product is being affected by the geometrical orientation, which has not been addressed so far. We just mask that region and perform the clear region. So that is the most unresolved area or gray area of microwave remote sensing. We are not dealing with the affected area, geometrically affected area. So as I said, it is the product, the unit of the product is backscattering. Okay? So sigma is a function of various sensor characteristics and target characteristics. So when you want to study one particular characteristics like dielectric constant through which you are going to measure the soil moisture, assume that. If you want to study the soil moisture, you just have to eliminate the influence of the other parameters from the sigma. That's all, simple. So that is how the basic simulation, you need to understand the basic simulation, how the basic simulation is performed on microwave remote sensing data products. So agriculture and SAR, I have listed a few application areas of SAR, but this is not actually limited. I've just listed a few important application areas where the microwave remote sensing has proven its fullest potential. So crop biomass, plant water content, plant height, leaf area index, crop phenology, soil texture, soil moisture, soil salinity, saline hot pans, and surface roughness. And these are all the few areas where the applicability has been completely proven. So we'll see one by one. So in order to find out the vegetation, the biophysical characteristics of the vegetation, the first kind of vegetation model have developed called RVI, Radar Vegetation Index. This is the first kind of vegetation model. Okay, Radar Vegetation Index that was developed based on the depolarization characteristics of the target, data. First kind of vegetation model. So this model, as I said, it is developed based on the depolarization characteristics of the surface. And Like as many of you aware of the simulation called NDVI, Normalized Differential Vegetation Index, which has been arrived from optical remote sensing data product, right? So the information you get it from the NDVI is not the absolute measure, it is a relative measure. You cannot able to extract the amount of biomass from the NDVI. It is a relative measure, it is not an absolute measure. The NDVI again has to undergo some other process to find out biomass and other biophysical parameters. Similarly, radar vegetation index will also be resulted in relative values but not the absolute values. The values will be ranging from 0 to 1, will describe the vegetation characteristics. If you want to further deep dive, then you need to perform this, you need to use this product for some other processing. So the next model is called DPSVI, Dual Polarization SAR Vegetation Index. And the previous model, Radar Vegetation Index, was developed only for quad pole information, quad pole data. If you have a quad pole data, no doubt Radar Vegetation Index will be used with high accuracy. But you know, in the data which is available nowadays, freely available is Sentinel-1, available in dual polarization. So when you lack in such kind of information, you need some other model to find out the vegetation characteristics. So that is why the DPSVI model has emerged. Because this model can be well executed only with quad pole information. Only with quad pole information, this model can be well executed, just similar to radar vegetation index. And this model has proven its potential along with both theoretically and practically. So the values are very close to the NDVI values and the radar vegetation index values. After this model, there are few models like DPRVI has also emerged for dual polarization. That is also a very good model to describe the biophysical parameters of the crops. So the inventor of DPRVI is none other than Professor Avik Bhattacharya sir. So that model will also work good to find out the biophysical characteristics of the crop. The next one is plant water content. We have a very popular model called water cloud model. So water cloud model is basically developed as a function of vegetation moisture and soil moisture. It's basically a function of vegetation and soil. If you take any data product, SAR data product, in copolarization, it will be a function of vegetation moisture and soil moisture. Obviously, as I told you earlier, if you want to study about the soil moisture, you just have to reduce the influence of vegetation moisture. If you want to extract the vegetation moisture, then you need to find out soil moisture, subsequently reduce the influence from the main product. That's all. So this is a well-proven model. However, this model, it doesn't take the influence of surface roughness. So it is a partially developed model because SAR data is being affected by surface roughness. So this model doesn't take that particular parameter into account. So these are all the maps which are arrived from the papers which are published. So the paper is listed down, okay? So through this water cloud model, this is a paper where the salt-tolerant vegetation index was developed. Salt-tolerant vegetation index. This particular model will identify the crops under healthy state, stressed state, and salt-tolerant crops as well. So based on the plant water content information and the soil salinity information, this particular model was developed, and this model will be resulted in the healthy, stressed, and salt-tolerant crops. And these are all the locations of the stressed and salt-tolerant crops. You can see it in the map. And this is most interesting work, crop phenology. And we have a lot of work to find out the crop phenology of the paddy crop. There are a lot of works you can see. There are a lot of works performed to find out the crop phenology. But this work is something different that we have only focused on delineating the crops under ripening stage. Because that is where the farmers in the coastal delta region are very much struggling during the cyclone time, because if their land is hit by the cyclone, they have to approach for the insurance. So they need to know the percentage of land under ripening stage. So this particular model is effective, very effective to find out the ripening stages of the crops. This model was developed based on the 3 parameters called DPSVI, GRD entropy, because in microwave remote sensing data products will be available in 2 modes, GRD and SLC. So GRD will have only the intensity information, and the SLC will have both phase and intensity information. So we just make use of these 3 parameters, analyze their interrelationship, and finally we simulated a model called PS3, through which you can able to find out or map, or you can able to map the areas under ripening phase or the crops under ripening phase. You can see the stage 3 got the positive value in the PS3 simulation. So the resultant product, when you find the positive values, it directly represents the crops under ripening stage. And this model has demonstrated, the potential has demonstrated with the field data with the accuracy percentage of 86. This is a very good percentage. And coming to the most important parameter in agriculture, soil texture, I think most of you are aware of this triangle, right? Through this triangle, one can able to find out the type of the soil. Only when, if you have the percentage of sand, silt and clay. If you have that, you directly plot the soil samples over the triangle so that you can able to find out the type of the soil. It is very essential. But think about if we can able to apply this model in remote sensing platform. If you want to apply this model in remote sensing platform, you need to have the data representing clay, data representing sand, data representing silt as a separate products, separate spatial products. Then only you can able to make this triangle, right? So this particular problem has been well addressed in the work. So in which, see, this triangle has been replicated with the remote sensing or microwave remote sensing based indices, HRMS soil to represent the sand, dielectric property represent the clay, and the correlation coefficient analysis between HRMS and sigma to represent silt. So it has been well modified with all these parameters, and we finally came out with a very nice soil texture map. And the next one is soil salinity. As I said, the potential of microwave remote sensing in analyzing the chemical characteristics of the soil is proven up to salinity level. Because if there is any contamination in the water or in soil, in the water in the soil, then definitely there is a loss in the signal. So that is the base. That is the base through which we can able to find out the level of salinity in the soil. So we have simulated this model. Look at this model. This model is a 3-dimensional simulation space through which you can able to find out the imaginary part of dielectric constant, which is nothing but the dielectric loss. The dielectric loss will directly represent the amount of salinity present in the soil. So this model was well proven for the free water, whereas in the clay water, this model finds a difficulty to produce the salinity level because, microwave remote sensing can work better when the salts are completely dissolved in the soil, which means high amount of free water content. When the soil is accumulated with high amount of free water content, this particular model can be well utilized. And salt tolerant vegetation index, that is what I have shown that slide, and this is the model, base model, and this is the result of that model. So this is again the another work. We have estimated salinity through DSDM model, that is fine. So when you want to find out the amount of salinity that has been induced by irrigation and upheaval process, there should be some model, no? So in this work, we have analyzed, we have selected 2 different data products, 2 data products acquired in 2 different times. One is in dry state, another one is in wet season. So in the dry season, what we'll do, we used to practice irrigation, right? Whereas in the wet season, because of the rainfall, we don't irrigate the soil. So in the dry season, we'll have effect of irrigation and upheaval process. Whereas in the wet season, soil will be only affected by the upheaval process. So if you minus the wet season influence from the dry season, you will get the irrigation-induced salinity. This is a very basic understanding. We analyzed it, we applied it and find out, and we segregated the amount of salinity induced by irrigation and the amount of salinity induced by upheaval process. And saline hot pans. So this is not the actual hot pan where you can find in the paddy field. Those are the natural hot pans. This is the artificial hot pan, saline hot pan, which is usually induced by the over accumulation of salinity at the root zone. So in order to define that, in order to segregate that, we have developed a two-dimensional classification plane, as I shown here, two-dimensional classification plane. So this two-dimensional classification plane resulted in 5 classes. Okay? So look at this class. This is a class of waterlogged vegetation. So when this two-dimensional classification plane has given third dimension based on the salinity values, then this waterlogged condition, you can find out the reason for this waterlogged condition, whether it is natural or it is salinity induced. Soil moisture, we have a lot of models, like it starts from Du Bois model. We often consider Du Bois model because it has practical applicability. You can able to use this particular model spatially. And this is a complete model, well-developed model, because it considers roughness. It considers a lot of parameters into account. So it is not a partially developed model like water cloud model. It is a well-developed model. So you can use your Du Bois model to estimate the moisture content. However, there is a problem in Du Bois model, that you can use this model up to 40% of soil moisture you can use. More than 40%, this Du Bois model may not be used. That is a major problem. Whereas we have other model for soil moisture called free water model. That model can be applied for the soil having moisture content more than 70%. You can understand. Few models work good for the soil moisture up to 40%, and few models work good soil moisture more than 70%. So there is a problem in the existing model that has to be properly rectified. So we have used machine learning because, see, whatever the simulation we used to implement on the SAR data, there is always an ambiguity, fuzzy, in delineating a proper threshold, in defining the threshold between the different classes, or defining a threshold between different variations or ranges. It will be a bit difficult. There is always a fuzzy in the empirical simulations. So we often use machine learning in microwave remote sensing data products to resolve the fuzzy. So as I told, the soil moisture, there are 2 products, free water index and the Du Bois model, which works at a certain percentage of soil moisture. So we have used machine learning technique. Just look at the figure, graph. Soil moisture, few models works good at the lower end and few models that works good at the upper end. So there is a problem, right? So we have used machine learning techniques to address this problem. And finally, we have arrived a proper result so that the soil moisture can be estimated irrespective of the heterogeneity in the soil moisture regime. So this problem has been well addressed with the machine learning techniques. See, this is the best model, we got it from machine learning. And always remember, there is a lot more to learn from microwave remote sensing, because microwave remote sensing is an ocean. Okay, it's an ocean. You always have a scope to explore. Thank you so much.
Thank you, Dr. Shobha Periswamy, for insightful session. We appreciate your contribution to the field and look forward to the impact of your work in agriculture.
Next, I would like to invite Dr. Feroz Samboli from DLR Germany to this stage for her presentation on agri-research with SAR approach.
So hi everyone, I'm very glad to present a bit of my work to you today. So before starting, I want to first introduce myself. I'm a radar scientist with a background in radio frequency systems and engineering and electrical engineering in general. And I'm working at the Microwave and Radar Institute, so at DLR, the German Aerospace Center. I got my doctoral degree from Karlsruhe Institute of Technology in synthetic aperture radar field. And I've been moving around during my studies a lot. So I did my bachelor thesis at DLR, and then I did an internship on hardware systems in Japan at Sony, and then a master thesis at Airbus Defense and Space. So I've been moving around, and this is something that I recommend to all of the students. So try different things every time. And I'm volunteering for Ieee Grss Syw. I'm the treasurer now, and I had many other roles beforehand. So I was the chair of young professionals, and I was the coordinator of webinars, and I've been involved in many conferences and events. So now let's talk about the technical things. So nowadays, natural disasters and hazards are becoming more frequent and severe. And like, for example, here, a collision with an iceberg, which happened in Alaska in September, and the Amazon rainforest fires, which are emerging a lot recently with 65,000 fire hotspots, and many maritime surveillance problems like piracy kidnapping in the Somali waters, which happened in March this year, with 20 crews being kidnapped. So those examples emphasize the need that we need a real-time monitoring of such high-risk areas. And this is where synthetic aperture radars come into play. They can deliver high-resolution images independently of the weather and during day and night, and they can penetrate on the Earth's structure, and they are independent of the distance. So it's not like a camera, so you can be further away of the Earth and get high-resolution images. And it's a complementary information to optical systems. So we can have SAR in airborne, in aircrafts, and on satellites, so it will be like a spaceborne system. And we can use SAR for many applications, like climate change, disaster monitoring, or environmental protection, like here there is this oil spill, and also agriculture. And now I will focus on agriculture, and I will use India as a use case, so because we are in India today. So the problem in India for agriculture, so India is a vast land, so it has diverse crop types and land usage, and which requires continuous monitoring. And also, there are many farmers which who have small fields, which we need localized data for that specific field and for precision agriculture. And we need a real-time monitoring. So some farmers want to know exactly now what is happening in their fields. So we need to have real-time data, real-time applications. And me talk about SAR first. So how can we use SAR for agriculture? So how can SAR image the world? So it transmits microwave signals to the Earth and gets the signal backscattered to the radar system. And that's how we use the backscattered signal to analyze the surface features. So we have a transmission and reception over an integration time, and then we have like some processing, and then at the end we get a 2D image. So the way the radar system works and the way we get the backscattered signal differs from the type of objects. So we have, like, for example, some vegetation fields which will be scatter the signal like a surface scattering, and volume scattering, it will be about trees and vegetation canopies, and we have also a double bounce scattering which is related to buildings and vertical structures. So how can we use SAR for agriculture? So I know many of you work in this field and know what can we monitor? So SAR can classify crop types, for example, and monitor their health and growth stages, and they can monitor shifts in the land usage and coverage, and also monitor the soil moisture changes and just detect if there are some things happening like droughts and flood impacts and so on, and there are many other applications as well. And at DLR, so we develop many multi-baseline SAR imaging agriculture a lot. So like the polarimetric SAR interferometry, which makes use of polarimetry and phase difference to measure the height of the canopy. And also the SAR tomography, which is a fancy method which place the satellites in specific baselines to have like a vertical scattering of the canopy. And also the holographic SAR tomography, which uses a circular flight of the satellite to monitor the area from different aspects angles. And the satellites are in different vertical baselines so that we get a 3D scattering of the vegetation. So now let's see how the SAR backscattering signal works for different parameters. So the signal that we get from the ground can differ from different parameters. Like, for example, if we have a high frequency, it will not penetrate as a low frequency, and the incident angles also influences the backscattered signal and the polarization, the geometry also. If we have a big tree, it's not like if we have a small plant, and the dielectric constant. If you have a dry tree or many water in the plant, so it's different. So it differs a lot on the backscattered signal. And here is an example of a corn and wheat field, so measured, for example, in July 3, and then after 3 weeks. And you can see here the reflectivity of the signal. It's different from one area, from one period to the next, and for the next. So you can see here the plants are higher, and they have more water, and that's why the backscattered signal will be higher. And they have different things for different frequencies. So what can we take out of this? So we have many parameters, and we have many things that change the backscattered signal, and we can make use of that. So, and this is actually the focus of my work. So I'm developing a cognitive synthetic aperture radar, which can interact with the environment so that it can percept, analyze the environment first, and then changes the transmission so that we can focus on only the things that we are interested in and have more precision. And it's based on the perception action cycle of a cognitive radar. And I'm using a high altitude platform which flies at a 20-kilometer height. So this platform is really attractive. It's still new, so we are developing this platform at DLR, and it has a long endurance. It can stay for up to 3 months during the flight, and it has a good coverage, and it's autonomous. It's like a UAV, so it's very nice for this application. And so if we are in front of this beautiful SAR image, so we as human, so we observe the image widely. But when something catches our attention, so our gaze focus on that specific thing directly. So we focus on, for example, this one. So this shape this is a river. So, and this is exactly what we want the SAR system to do, to mimic the visual cognitive cognition of the human. And for this, so the SAR will have a machine learning implementation on the fly, so it can think and decide on the best way to observe the environment during the fly. And how it works for SAR, so the first mode is a map search mode. It runs continuously during the flight with low performance, and onboard data evaluation will be done. And once something is interesting, for example, interesting to the user or to the application, then another mode will switch on with high performance and will automatically activate data acquisition with more details and more adaptive parameters. And then the relevant information will be downlinked to Earth. So this will decrease the data a lot, and this will have a better data latency. And So how does it work? So we have a lot of parameters that we can extract from a wide observation. So we can have a RAD observation of the canopy, the change detection, the backscattering behavior, and this run into a cognitive decision maker, which will give us the best polarization, for example, or the best frequency, or the best elevation angle, so the look angle of the radar, and the energy. And that in that way we can have we can focus on key areas for enhanced agriculture insights, and we can have a real-time observation because we are adapting the parameters on the fly to have reduced data and also an adaptive observation. And in this way, we can have a real-time field monitoring via smartphone, so the farmers can get the details automatically afterwards. And this is based on a learning algorithm that can learn from itself and evaluate the environment first and then adapt the system with the parameters of the radar on the fly. Yeah, that's it, and thank you so much.
Thank you, Dr. Feroz, for your enlightening presentation. Now, I would like to hand over the mic to Dr. Mosmi.
We are done with our first half of the session. By 12:30, we'll start our lunch. Before that, I would like to invite everyone for the group photograph. Yes. Yes. Please feel free to collect your certificates from Dr. Shubrangi at the corner of this table.